joules. Joules is meters per second squared times mass times kilograms. So the kilograms cancel each other out, and then you're left with seconds. So the kilograms cancel each other out.
Seconds cancel out. Meter cancel out 1 meter,
And then
wait.
I feel like you're left with more seconds. Where do you get the kilograms per meter squared? Where do you get this meter squared from?
Okay, 1 Newton. Newton is mass times acceleration. Force is mass times acceleration.
Yeah.
Mass in kilograms. Meters per second squared is the acceleration.
Yeah.
Multiply that by distance to get energy.
Right.
So
right.
meters times meters gives you meters squared. And then everything cancels out.
Yeah, that okay. So the mistake I made a mistake of just looking at newtons. So I have to go with the extra step to joules.
Woo-hoo. Okay, there we go.
That would be a good question actually on an exam.
I don't think they'd ask something that tough.
It's not that tough to calculate the units though. Like, if you thought about it a little bit. I mean, I was trying to do that in my head.
All right, so when do we use this 1/2? On one end, we've got E equals mc squared, and on the other end, we've got Ek equals 1/2 mv squared. So energy is mass times velocity squared, or energy is 1/2 mass times velocity squared. It doesn't really make a lot of sense. The issue is that E in the E equals mc squared is considered rest mass. Okay, it's considered the mass of an object not moving.
Not moving.
That's right. E equals mc squared is its conversion from rest mass to energy.
But
The energy that an object not moving has.
so then why would you multiply by a velocity at all if it's not moving?
That's just the conversion factor. The c squared is the conversion factor from energy to matter.
Oh,
Okay. When you have the total energy of an object, okay, is its kinetic energy plus its rest energy, that mc squared. Now, what ends up happening is that for large, where am I here? In other instances, every case, since the c is the speed of light, it seems that we have 2 different equations for the kinetic energy of a particle. One has multiple quantities, while the other doesn't. The reason for this discrepancy lies in advanced math behind special relativity, and it's too complicated to get into. Okay, but that graph that's on your page that doesn't print off on mine kind of shows you the difference. The total energy of a particle is, or of any object, is actually this gamma mc squared, where gamma, if we're doing special relativity, I would explain to you, which is it's a ratio of the object's velocity to the speed of light. And the simplified kinetic energy, 1/2 mv squared, holds true up until we get to about half the speed of light. Okay, so to make a long story short, an object's kinetic energy is fine to express 1/2 mv squared for macroscopic molecules. As soon as you're talking about photons, you only use E equals mc squared. And that's the only time for any electron, molecule, anything like that, you use the standard kinetic energy is 1/2 mv squared, just like we use for the electron. Yeah. You won't be. Okay, you won't be. It'll be, or you would ignore the effects of relativity, unless you're choosing to do the relativity option, in which case you don't ignore the effects of relativity. No, there's an SL relativity option, and it's tough. It combines relativity and particle physics all in one.
No.
It's
no.
it's the longest of all the options.
So it's like this close to being the HL axis.
Yeah, yeah. I don't know why they would combine those two together. That seems very silly to me. Anyways, okay, let's do one more question from the textbook here. So get out your textbook, page 396, number 5.
It's just that. So you can just get the questions.
Go, man. Let's just go. Yeah. Yeah, sit at the back, right behind Josh.
Great. Josh, don't be able to grab the Let's take a look at. Oh wow! I flipped right to the special events.
Not go too far because we don't really. Which page is that?
Page 396, number 5. Sure, read out part A. 5A.
What is the effect of the intensity of light in the photoelectric experiment?
And Abdul, why don't you answer 5A
What is the difference?
of the intensity of light in the photoelectric experiment? Visualize that simulation, turning up the intensity of the light without changing the frequency. What did that do? Increase the what? Good. I'm going to break that down a little bit farther. But there's a caveat to that. Josh, what do you think the caveat to that is? It'll only increase turning up the intensity of the light will only increase the number of ejected electrons if, wait,
Still caveat, please.
C-A-V-E-A-T. Caveat.
Okay.
Increasing the intensity of light will increase the number of ejected electrons. Only if someone help him out. Adam?
Yeah, the frequency of light is greater.
Boom. I like it. Only if the frequency of light is great enough to actually start knocking the electrons out of the orbital shells. Alright, part B says, to determine the work function of a given photosurface, the light of the wavelength 2.3 times 10 to the negative 7 meters is directed at the surface with stopping voltage Vs recorded. When light of the wavelength 1.8 times 10 to the negative 7 meters is used, the stopping voltage is twice as large as the previous one. Find the work function.
Yeah.
Okay. It goes back to the graph of frequency versus energy. Okay, so I'm going to re-sketch that graph. I don't know why I deleted it at the beginning of this. Alright, re-sketch the graph. Let's do it over here. What was that? Oh my god, what's going on? Glitchy!